So we are going to take the derivative of this equation with respect to t. That is not a variable in the equation. It's a separate variable. So what that means is when I take the derivative of anything in this equation, I have to do so with respect to t, which means since that variable is not the variable we're taking the derivative with respect to, I'm going to have to put something beside of it. So if I take the derivative of v, it is just 1, right? I can write the 1 if I want, or I don't have to, but I'm taking the derivative of v with respect to t. So I would put a dv dt right there with that v when I take its derivative. And then I've got 1/3 pi. That is a coefficient. I'm going to leave it out front. And then I've got r squared times h. What am I going to have to use to take that derivative? Got to use the product rule for that. So I'm going to put some parentheses here. I'm going to do r squared times the derivative of h. What is the derivative of h going to be? It is 1. What do I have to put with it? It'll be dh dt plus, then I will have h times the derivative of r squared, which is 2r. What do I have to put with that? Not dv dt, dr dt. So basically, whenever we do implicit differentiation, we only had to put the dy dx with the y's, because the x, we were taking the derivative with respect to x, right? In this equation, we're taking the derivative with respect to t, which is not even in the problem, right? So every time we take a derivative, whatever variable we are taking the derivative of, we have to put d whatever over dt with it for that. So if we simplify this a little bit, I'm not going to go far with this, dv dt equals, is it okay, you guys, if I make that pi over 3, times r squared dh dt plus 2rh dr dt. Now, if this were a question that I was asking you and not just an introduction, this problem would give you information about the radius and the height at certain points and rates and different things, and we plug some numbers in here. This one's just setting up. I want us to just talk about what each variable means here for this, so we can kind of understand what's going on. So my let's just do our r, our h. Our r is our radius of the cone, and it would be the radius of like the water in the cone, right? It would, because not just the tank, it's not the constant, because the tanks stay in the same size the whole time. We're talking about the amount of water, because as we fill up that cone, the radius of that water is going to get bigger and bigger, and the height will get bigger and bigger. So radius, I didn't put units on this, but let's put some units on this. Let's do feet and seconds. Okay, we'll use feet for our dimensions. So radius would be measured in feet, and height would also be measured in feet. Okay, and volume is actually not, volume's only in the original, because when we take the derivative it kind of goes away, but what would my volume be measured in if my radius and height are measured in feet? Not feet per second. Feet per second would be a rate. It is not feet squared. It is feet cubed. Feet squared would be like a square foot, like a tile on this floor. When we're talking volume, it's got to be cubed. So, feet as well as volume. All right, so radius, height, those should be very straightforward. Volume is cubic feet, and we're probably recalling that that would be the case here. So let's talk about these other things here. I got a dV dt. Okay, this is the derivative of volume with respect to time. Okay, so dV, let's use colors here. dV dt would be the rate that volume changes with respect to time. What are units for that? Feet cubed per second, because volume is feet cubed, and it would be per second because it's a rate. So it'd be feet cubed per second. Okay? All right. Then I've got this dH dt here. So dH dt would be the rate that height changes with respect to time. What are the units on that? That one's feet per second, because height would be measured in feet, and that'll be changing per second. And then the last one here is your dr dt. That is similar to height. Your dr dt would be the rate that the radius changes with respect to time. And that would be also feet per second. And these problems are called related rate problems because how fast the height and the radius are changing are related to each other, but they're not necessarily the same. If our volume is changing at a constant rate, we already said the height will change quickly at first and then more slowly towards the end. So our volume might be changing at a constant rate, but the height would not be for that. So now this is just kind of looking at what all of these mean. I'm not asking you a question yet. We will eventually get to ones where this is asking you a question. We're going to stop here with this for right now. The second one we're not going to do anything with. I just want you to see it because I think it's cool. So several of you are lifeguards in the summer. So here's our pool that we have here. This swimming pool is shaped like the one below. This is a kind of classic shallow end, deep end sort of swimming pool here. And it has a leak that is causing the height of the water to drop 9 inches per day. So you, as a lifeguard, once the leak is discovered, the lifeguard gets out the water hose and starts filling the pool with a water hose that adds 6 gallons per minute to the pool. How long will it take for the pool to drain or overflow? Assume that a heavy rain has just filled the pool to full capacity. Assume it does not rain anymore until the pool is drained or overflowed. So if your pool is full, also ignore evaporation, which you can't really do, but you need to be able to do this problem. So we're not going to do this problem right now. This is a very complicated problem because the shape of this is weird. So it makes it complicated if you were to actually do this. But water is leaking out of this pool. You know how fast the height is dropping, but you don't necessarily know that you're losing this many gallons per minute, right? You could pretty easily measure how many gallons per minute the water hose is pumping into the pool, right? You could grab you a gallon jug and measure how long it takes to fill it up. It would not be that difficult, but you probably don't know where this leak is. We're also going to probably assume that leak is at the bottom of the pool, because if it is at the top of the pool, like if the leak is right here, the pool's only going to drain to the leak area, right? But if we got a leak in the bottom of the pool, you're not finding that easily, and you're definitely not. It's leaking into the ground, and you're not going to be able to see how fast it is leaking. So the 6 gallons per minute, it really depends on how fast that leak is, whether or not your 6 gallons per minute is going to be, it could be the same as the leak, in which case the pool would just stay where it's at. If it's leaking faster than you're filling it up, eventually the pool's going to drain completely, even though you're putting water in it, right? If that 6 gallons per minute is actually faster than your leak, eventually you're going to overflow the pool because you're putting water in faster than it's leaving. So you could set up a formula for this. You could figure out what would be the case with the information that you have here. You could figure out if the pool is going to drain or overflow, and you could even figure out what time that's going to happen. Roughly, you have to ignore evaporation and rainfall and things like that. But this is an example. Certainly, any of the lifeguards at the pool, you guys been doing that at the pool? Probably not, right? Like a lifeguard's probably not going to do this, but if you're looking at something different, like an industrial sort of tank of some sort, certainly that could be something that you would run into. I think these are kind of cool. It might not be a leak. It might be something like you're pumping water out at the same time something else is going in. There could be all kinds of applications for this sort of stuff. So that's just an example of like where you could go with this for this problem. Now, there's some application. Now we're going to do zero application. It does make the problems a lot easier to do when there's zero application, but it's very much not interesting. Okay, so we're just going to look at some naked problems right now. They've not got any context, and we're just going to work on the mechanics of doing these problems. All right, so it says, given y equals x squared plus 3, find dy dt when x equals 1 if dx dt equals 2 when x equals 1. Okay, so we're given an equation, and notice that they give us information about dy dt, x equals 1, dx dt, and then we also have x equals 1. So we are looking at the point where x equals 1. However, my rate of change is not going to be the same at every point on this graph. So as x changes y, as the time changes, x and y are both going to change. So if I have variables that are changing, I cannot do anything with, I cannot plug any numbers in until I have already taken the derivative. So if I take the derivative of this, and because we have dy dt and dx dt, it's not asking us to do a dy dx here. We're asked to do a related rate problem where we have this third variable that's not in the problem, that is this t, right? So when we take the derivative of y, the derivative of y is just 1, but we must put dy dt with it. And then we must take the derivative of x squared, which is very simple. It is 2x, but we must put dx dt with it. Okay. So now, once I have taken my derivative, and then derivative of 3 is 0, so it just kind of goes away. Once I have taken my derivative, now I can plug information in to find what it's asking for. So it says find dy dt. That's what we're looking for. Dy dt is what we're looking for. So we are not replacing dy dt with anything because that's what we're looking for. We're solving for that. It tells us when x equals 1, so x is going to be 1. It also gives us the information that when x equals 1, dx dt, right here, is 2. Right? So dy dt, we're not replacing. It stays right there. Then we've got 2. Our x right here equals 1, so we plug it in. Dx dt equals 2, so we plug that in. So we end up with dy dt equals 4. And that would be our answer. Okay, so basically you are taking your derivative, making sure that you put the x dt's and dy dt's or dz dt's, whatever variables you have, with everything when you take the derivative, and then you're plugging in the information that they've given you. They should have hopefully given you enough information to figure out what that value would be that it's asking you for. Okay. Right now, we're not worrying about units because these are not in context of anything. Right now, we're having to set up the original problem, so that makes these a little bit easier. So let's do one that's a little bit harder for the derivative. Not terrible, but a little bit more difficult. All right, so we've got x squared plus y squared equals 16. It's asking us to find dx dt, and it gives us some information. So whenever we see that dx dt, that should tell us we've got to take the derivative of this with respect to t. So the derivative of x squared would be 2x, and with it we must put a dx dt. And then the derivative of y squared is 2y, and with that we must put dy dt. And the derivative of 16 is 0, so we just have a 0 here. Okay, so if we start to look at, once we take that derivative, we're looking for things we can plug in. So definitely, I've got an x equals 4. Actually, let me go back. I'm going to use green for what I'm looking for. So what I'm looking for, it tells me to find dx dt. Dx dt is what I'm looking for. I'm not going to replace dx dt. It needs to stay in the problem. Everything else, the x, the y, and the dy dt, all need to be replaced. So it gives us some of those. It gives us x equals 4. So this x right here, we're going to put a 4 right there. It gives us that dy dt equals 3 when x equals 4. So dy dt is going to be 3. We've got that. But what variable do we not know? Y. How could we find it? Yes. We can go back to the original. So for the y that we're looking for here, we need to find this y, but we don't know it. So we can go back to the original. We know x equals 4. So we could do 4 squared plus y squared equals 16. So that's 16 plus y squared equals 16. I'm going to subtract 16. I'm going to get y squared equals 0, so that tells me y is going to equal 0 for that. So now I have all the pieces that I need to plug in. So I will do 2 times, that x is 4. I'm going to put a 4 right here. The dx dt is what I'm looking for. I'm not going to replace it. And then I'll have plus 2. The y is 0. And I've got dy dt is 3. And this will equal 0. So that gives me 8 dx dt plus 0 equals 0, which is just 8 dx dt equals 0. I would need to divide both sides by 8. and we actually just end up with dx dt equals 0 for that. And that would be our answer. Okay, questions here? Yes? You can if you want, yes. Yes, so depending on the problem, sometimes that might be easier to do. You can like solve for that and then plug numbers in. But it can work either way, whichever one you want to do. All right, this one's a little more complicated. This is also going to, we have not in a little while, we've been doing a lot of theoretical stuff. We've not been doing a lot of just like taking derivatives and practicing those product rules and quotient rules and all of that stuff. This is going to bring us back to doing a little bit more of that. So if I want to take the derivative of 2xy, what have I got to use? Product rule. So I'm going to have 2x times the derivative of y. So that is dy dt. You might be in the habit of wanting to call that dy dx because that's what we would do if it was implicit differentiation. But this over here where we've got dy dt indicates that we're taking the derivative with respect to t. So we got 2x times dy dt plus y times the derivative of 2x is 2. And what do we need with that? Dx dt. So anytime you take the derivative of any variable, it's got to have the d whatever dt with it. All right, that's only my derivative of 2xy. Now I have to take the derivative of y squared, which is going to be 2y. What does that need with it? dy dt equals derivative of 8x is 8. What does that need with it? Dx dt. And let's clean that up a little bit before we start plugging things in. We've got 2x dy dt. We could. Let's do that. I like that. Everything is divisible by 2, so that's fine. So if we divide everything by 2, we're not going to have those 2's there. Y dx dt plus 2y dy dt equals, and we're dividing by 2. Oh, wait. I didn't divide that one by 2, did I? Don't put that 2. And then we'll get 4 dx dt. Okay, you don't have to divide by 2, but I do like doing that because that gives you fewer numbers you got to worry about getting in the right place. Now, are any of those common terms that we could put together? They're not. We got an x dy dt, but our dy dt over here has a y with it, right? Then we got a y dx dt, but this one over here doesn't have a y. So we don't have any common terms. So like, for example, on this one, Avery, I would probably not try to solve for a variable on this one because you've got so many different variables you can. But I would probably just start plugging in because once you have numbers in there, it will be easier to deal with. So let's look at what we can plug in. First of all, let's figure out what we're trying to find. We are trying to find dy dt. So dy dt, I've actually got in 2 places right here, dy dt. I'm not replacing those. Those stay where they're at. I know that y equals 1. So y, right here in both of these places, is going to be 1. I know dx dt is 5 whenever y equals 1. So dx dt goes here and here. Do you guys see any other variables that we can't plug in for yet? We're missing the x, right? So since we're missing that x, just like we did on the last problem, we need to go figure out what x could be. Because we've got to plug in numbers for everything except for dy dt. So whenever you're looking for a number, you're going to go back to the original equation if it's not given to you. So I know y equals 1. So I'm going to say 2x times 1 plus 1 squared equals 8x. So that is going to be 2x plus 1 equals 8x. And I've got to get those x's together, so I'm going to subtract that 2x. 1 equals 6x. And I'm going to divide by 6. So x equals 1/6. So I can now plug in. I've got 1/6 times dy dt. I do not want to replace. Plus my y is 1. My dx dt is 5. Got another y here. That's 1. dy dt. I do not want to replace. And then I've got 4 and dx dt is 5. Okay. So to simplify this, I've got 1/6 dy dt plus 5 plus dy dt equals 20. I definitely want, I'm going to subtract this 5, and I'm going to put 1/6 dy dt and 1 dy dt together. So 1 plus 1/6 is going to be like 6 over 6 plus 1/6, which is going to give me 7/6. So 7/6 dy dt is going to equal 15. And our last step is going to be divide by that 7/6, or 7/6. I'm dividing fractions. It's easy as pie. Flip the second, multiply. I'd probably multiply by 6 over 7. Cancel this over here. Multiply by 6 over 7 here. And so I'm going to get dy dt equals, that's not going to reduce, so what is 15 times 6? 90 over 7 would be our answer. Okay. Alright, questions on that? Alright, I do want to do, your homework is going to be like this tonight. Just so we get like a taste of the real thing here, of seeing like what types of problems we're going to use this for. I do want to do one application problem. If you get a little bit lost, don't worry about it too much, because you are just basically going to be doing that middle stuff for homework. But I do want to do one application problem real quick. So this is one of those application problems that's specifically made for math class. Like, it is an application, but not sure exactly where in the real world you're going to do this exactly, but the idea hopefully can carry over for this. So in a rectangle, the length is 8 foot longer than the width. Oh, wait. I'm remembering that this is not a great problem. Why is this not a great problem? Other than you just don't want to do it. No, we're okay with that. I say length is 5 feet. The length is 8 foot longer than the width. At 5 feet, what is the length of the width? -3. Does this make sense? No. Let's make that 10 right there. So change that to 10 in this case, so that we have something that could possibly make sense in the situation. we have area of a rectangle. And if we notice, I used the L right here and it really looks like a 1. Notice the information, like if we're finding the area of a rectangle, it is length times width, right? However, do you guys see any information about a width anywhere? Do we know dw, dt, or the width? Right. So we could try to like figure this out and like take this derivative and figure this out, but there is a better way. And that is to say the length is 8 foot longer than the width, which means length equals 8 plus the width. Now, I would really rather have everything in terms of L's because I got L, I got dl dt, I know that information, right? So if I solve this for my W, so I subtract 8 from both sides, length minus 8 is going to equal my width, then I could plug that in right here. And my area would equal length times length minus 8. And I'm going to distribute that and get L squared minus 8L. Now the problem can be done with the W, but it gets really complicated if you do because you don't have a lot of W information, right? But we do have a lot of information about this L. So now if we take the derivative of this, dA dt is going to be 2L dl dt minus 8 dl dt. And I need to change, I didn't change this 5 feet up here to 10 also. I need to change that in both places. So if I do it this way, I don't have to worry about plugging back in and figuring out what my width is. I can just take my derivative. Now I can just all plug in L's. So, the question says find the rate at which the area is changing. Which variable is that in my equation? What? Nope, it's not length. Find the rate. What is this? Rate at which the area is changing. Rate of the area. What was it? It's not volume, it's area this time. Because this is not like a 3D figure, so it wouldn't have volume. It's not going to be area squared. It's going to be your area per second. What variable in my equation is the rate at which the area is changing? dA dt. This is what you're looking for. You're looking for dA dt. So rate of the area is dA dt. So you're going to plug in information for everything else. So 2, we're doing 10 for that L because I messed the problem up. dl dt is 5 minus 8 times 5. And we will get, let's see, 100 minus 40. So our dA dt is going to be 60. What are the units? It is not feet per second. This is the rate at which the area is changing. How do we measure? No, not feet per second. How do we measure area? Length times width, which would give us square feet, right? So feet squared is area, but since it's a rate, it's going to be square feet per second. So think about whenever, like, you can kind of do like we've been doing when you're finding dA dt. Think about how area is measured. Area is measured in feet squared. So that's your change in your y over dt, how your time is measured, and it would be seconds for this. Okay. You won't have to do this tonight. We're going to look at that more tomorrow on doing more, well, not tomorrow, Wednesday, on doing these problems in context. Tonight, you just have naked problems. You're going to do, wait, I think I actually might want you to only do part A from all of them. Let me see. 194. Is that right? 194. Yeah, let's just do A for all of them. We'll be fine. Because it mixes it up, yeah. So you can just do part A only on all of them. So if you just want to write down 1 through 8, part A. Part B is just like the same problem, but you're plugging in different information, so I'm not going to have you do that. It's kind of repetitive. All of these are naked problems. So you're just taking the derivative, plugging in information that you have on those. Okay? So you got about 10 minutes. Go ahead and start those.